Here is a fact that should not be true. The universe is 13.8 billion years old. Light, the fastest thing there is, has had exactly that long to travel. So nothing we see should sit farther than 13.8 billion light years away. And yet the edge of what we can see lies 46 billion light years off in every direction, more than 3 times too far. The universe is younger than the distance across it. That is not a mistake, and it is not faster than light travel. It is something far stranger, hiding inside the most ordinary fact about space. Tonight, we'll walk to the bottom of it. So dim the lights, get comfortable, and hit subscribe. The answer rewrites what the word distance even means. Part 1. 4 questions hiding inside one. There is a question that sounds so simple a child could ask it, and so simple that you might think it has a single, clean answer waiting somewhere in a textbook. How big is the universe? It feels like it belongs in the same family as how tall are you, or how far is it to the next town. You expect a number. You expect that somewhere, someone wrote that number down, and that tonight I am going to tell it to you, and you will nod, and we will move on. I want to be honest with you right at the start, because honesty is more interesting than a tidy lie. There is no single number, there is no one answer. And the reason there isn't is the whole story we are going to walk through together tonight. The truth is that the question, how big is the universe, is actually 4 different questions wearing the same coat. There is the size of the part we can see. There is the size of the part we could ever reach or touch, even in principle, even with all the time in the world. There is the size of the whole thing, the seen and the unseen together. And then there is the strangest question of all, the one about whether there is anything beyond the universe at all. These 4 sizes do not agree with each other. They disagree by amounts so large that no human mind, including mine, including the minds of the people who measure these things for a living, can actually picture the gap between them. Let me give you one of the numbers now, just so it is sitting in the room with us, even though I am not going to explain it yet. The part of the universe we can see, the part astronomers call the observable universe, is about 93 billion light years across. Hold that loosely, because here is the first strange thing I want you to notice. That number is somehow both far too big and far too small to be the real answer. Too big because nothing we will ever visit lies anywhere near its edge. Too small because the true universe almost certainly dwarfs it and may not have an edge at all. And there is a paradox folded inside that number that I want to plant in your mind now, like a seed, so it can grow quietly in the background while we talk. The universe is 13.8 billion years old. We are fairly confident about that. Light, the fastest thing there is, has had 13.8 billion years to travel. So you would expect the farthest thing we could possibly see to be about 13.8 billion light years away. Instead, the edge of what we can see sits roughly 46 billion light years away in every direction. The universe is younger than the distance we can see across it, by a factor of more than 3. That should be impossible. By the time we are done tonight, you will understand exactly why it is not only possible, but unavoidable. I want to be clear about what we are doing here, because this is not really a video about feeling small. Feeling small is easy and a little cheap, and you can get it from a single nice photograph of the night sky. What I am after is something slower and stranger. I want to walk you up a ladder, one rung at a time, where each rung is a size, and at each rung your ordinary intuition, the sense of bigness you carry around from living on the surface of one planet, quietly stops working. Not all at once, not with a shock. Just gradually, the way your eyes adjust in a dark room until you look around and realize the room was never the shape you thought it was. So, settle in. Get comfortable, however you like to get comfortable when you are going to be here for a while. This is a long climb, and I'm going to take it at the pace of a late-night conversation, because that is the only honest pace for a subject this large. There is no rush. The universe has been this size for billions of years. It will still be this size when we reach the top of the ladder. Here is the shape of the climb, so you know where we are going. First, we are going to build the ladder from the bottom, starting at your own feet, because the number at the top means nothing until the rungs below it mean something. Then we are going to face that paradox I just planted, the one where the universe is bigger than its own age, and we are going to meet the engine responsible for it. After that, we will reach the edge of what we can see, and discover that the edge is not what anyone expects. And finally, we will ask what all of this does to you, the person watching, the small warm thing on the small warm planet, trying to hold a number this size in your head before you fall asleep. I want to give you one more idea to carry up the ladder, because we are going to use it the whole way. Picture the universe not as a single box with you somewhere inside it, but as a series of bubbles, each one nested inside a larger one. The bubble of what you can see from your window, the bubble of the solar system, the bubble of the galaxy, and eventually the bubble of everything light has had time to reach you from. Each bubble sits inside the next, and here is the part that will matter enormously later. Every single person watching this, and every creature anywhere in the universe that has eyes and a sky, sits at the exact center of their own bubble. There are billions of centers. There is no one true center at all. Your bubble and mine overlap almost perfectly, because we are close. But somewhere out there are bubbles that share nothing with ours, not a single star. There is one more thing worth admitting before we start climbing, and it is a little reassuring. Nobody can really picture these sizes. Not me, not you, not the astronomers who spend their lives measuring them. The human mind evolved to judge distances we could walk, throw a stone across, or travel in a day. It is superb at the scale of a valley or a coastline, and completely lost at the scale of a galaxy. So when a scientist says the universe is 93 billion light-years across, they are not picturing it either. They are holding a number and a chain of careful reasoning, and trusting the mathematics where the imagination gives out. What we are going to do tonight is build that chain together, link by link, so that even though you will never be able to truly see these sizes in your mind, you will understand exactly how we know them, and where, honestly, our knowing runs out. That is a different and better kind of understanding than a single memorized figure. I am not going to answer the title's question tonight in the way you might expect, with a final figure you can write on a card and file away. By the time we reach the top, how big is the universe is going to feel less like a fact you memorize and more like a door that will not quite close, no matter how gently you push it. And I think that open door is a better thing to fall asleep next to than any number could ever be. But before we can talk honestly about 93 billion light-years, we have to do something much smaller and much harder. We have to make a single light-year mean something. And that, surprisingly, starts not out among the stars, but right here, at the bottom of the ladder, close enough to touch, is less than break time equals 1s, is greater than, number, part 2. The ladder starts at your feet. Let us start with something you can actually feel, because everything that comes after depends on it. Take a single step across the room. That distance, the length of one ordinary stride, is something your body understands without thinking. Now hold that feeling, because we are going to climb away from it so fast that within a few minutes it will seem almost laughably tiny, and I want you to remember that it once felt normal. Step back from yourself until you can see the whole Earth, the way the astronauts did. The planet you are lying or sitting on is about 8,000 miles across. Light, which we are going to use as our ruler for the rest of the night, could circle that entire planet about 7.5 times in a single second. To you, the Earth is the whole world. To light, it is barely a speed bump. This is the first quiet lesson of scale, and it is going to repeat at every rung from here on. The thing that feels enormous to you is, at the next level up, almost nothing at all. Now, go to the moon. The moon is the farthest place any human being has ever stood, and in the story we are telling tonight, it is practically in our laps. The moon is about 250,000 miles away, which sounds like a lot until you measure it in light. Light crosses that gap in a little over 1¼ seconds. When you look up at the moon, you are seeing it as it was about 1¼ seconds ago. That is the first appearance of an idea that is going to grow and grow until it swallows the whole video. You never see anything as it is. You only ever see things as they were, because light takes time to arrive. The universe does not show you the present. It only ever shows you the past. Go further. Go to the Sunday. The sun is about 93 million miles away, and its light takes 8 minutes and 20 seconds to reach your eyes. Sit with that for a moment, because it is genuinely unsettling once you really feel it. If the sun were to simply switch off right now, this instant, you would have no way of knowing. You would feel the warmth on your skin. You would see the light in the sky for 8 more minutes, completely unaware that the source was already gone. The sunlight falling on you tonight, or this morning, left the surface of the sun before you sat down to watch this. We are all living, always, 8 minutes behind the sun, and millions of years behind the stars, and we will get to just how far behind in a little while. Keep climbing. Walk out through the solar system in units of light time, because miles have already stopped meaning anything. Light reaches Jupiter in about 43 minutes. It reaches Neptune, the outermost major planet, in about 4 hours. So if you wanted to send a message to a probe near Neptune and get a reply, you would wait the better part of a day for the round trip, and you would not be able to do anything to hurry it because nothing in the universe travels faster than that light. Then go further still, past the planets, to the farthest object human hands have ever made. The Voyager 1 spacecraft, launched in 1977, has been flying away from us for about 48 years. It is the most distant human object in existence, and after nearly half a century of travel, it is still less than 1 light day from home, not 1 light year. 1 light day. Light covers, in a single day, the distance that took our fastest far-flung space traveller almost 5 decades to cross. I want to let that land, because this is the first rung where the ladder starts to feel genuinely strange. We tend to think of our spacecraft as fast. They are not fast. Compared to the distances we are about to discuss, they crawl. If Voyager 1 were headed toward the nearest star, which it is not, it would take roughly 73,000 years to get there. 73,000 years. All of human civilization, every city ever built, every word ever written, fits comfortably inside that span, with room to spare. That is the gap to the very next star, the closest one of all. But the solar system does not end at Neptune, or even at Voyager. It ends, if it ends anywhere, at a faint, enormous shell of icy bodies called the Oort cloud, which may stretch as much as 1.5 light years out from the sun in every direction. Think about what that means. The true edge of our own solar system, our own cosmic backyard, may sit 1/3 of the way to the nearest other star. Our backyard is so large that it nearly touches the neighbours. And between us and that neighbour, there is almost nothing. Not a little. Almost nothing at all. The nearest star to the Sun is Proxima Centauri, and it sits about 4¼ light years away. Here is a way to feel that emptiness. Imagine the Sun shrunk down to the size of a basketball, sitting in a city, let us say in New York. On that same scale, the nearest star, that basketball-sized neighbour, would be sitting in Australia. And between those 2 basketballs, across an entire planet of distance, there would be essentially nothing but a few specks of dust. That is the real texture of the universe. Not a sky crowded with stars, the way it looks from a dark field at night. The closeness of the stars in the night sky is an illusion of perspective. The reality is staggering, almost frightening emptiness, with the rarest scattering of light strung through it. This is the second quiet lesson, and it is more important than the first. The bigness of the universe is mostly the bigness of nothing. When people say space is large, they usually picture more stuff, more stars, more galaxies. But the truth is the opposite. Space is large because it is mostly empty, and the stuff is the exception, the rounding error, the rare island in an ocean that is almost entirely water, with almost no islands at all. Let me give you one more way to feel the emptiness, because it is the thing people most consistently get wrong. When you look at a photograph of a galaxy, you see a glowing disk that looks crowded, packed edge to edge with stars, like a city seen from above at night. But that is an illusion of distance, the same way a forest looks solid from far away, even though you could walk between the trees. If you were standing inside a galaxy, which you are, you would find that the nearest star to any given star is typically several light years away, across emptiness so complete that if two galaxies pass straight through each other, which actually happens, almost none of their stars would ever collide. The galaxies would slide through one another like two clouds of gnats meeting in a stadium, the individual specks almost never touching. That is how much room there is between the points of light. The universe is not crowded. It is the emptiest thing there is, with the rarest sprinkle of matter hung inside it. So let us name our ruler properly before we climb any higher, because we are about to need it constantly. A light year is the distance light travels in 1 year, moving at the only universal speed limit there is. It is both a distance and, secretly, a measure of time, because to look across a light year is to look 1 year into the past. Carry that double meaning with you. It is going to become the most important tool we have. And here is the rung that should make you dizzy, the one that ends this part of the climb. Light takes a little over 1 second to cross to the moon, 8 minutes to reach the sun, 4¼ years to reach the nearest star. How long do you think it takes light to cross our own galaxy? Just our one galaxy, the Milky Way, about 100,000 years. A beam of light leaving one edge of our galaxy would not reach the other edge until 100,000 years had passed, longer than our species has existed in its current form. And that galaxy, that 100,000-year crossing, is a single dot, one island, in a cosmic map built not from galaxies, but from clusters of galaxies, sheets of them, walls of them. So the question that pulls us up to the next rung is this. If one galaxy is already too large to cross in the entire history of humanity, then what on earth arranged those galaxies into structures so enormous they make a galaxy look like a grain of sand? And who, or what, drew the map? Is less than break time equals 1s is greater than number, part 3. The architecture nobody designed. Let us pick up exactly where we left off, with our galaxy shrunk to a single point of light. Zoom out until the entire Milky Way, that 100,000-year crossing, that island of a few 100 billion stars, is nothing more than one dot on a far larger chart. Now the obvious question, the one we ended on, becomes pressing. When you connect the dots, when you map where all the galaxies actually sit, what shape do they make? Because if the universe scattered its galaxies at random, like sand thrown across a floor, that would be one kind of universe. But it did not. The galaxies are arranged, and the arrangement is one of the strangest and most beautiful facts in all of science. Start close, with our own neighborhood. The Milky Way is not alone. It belongs to a small gathering of galaxies called the Local Group, a few dozen of them bound together by gravity, spread across about 10 million light-years. Most are tiny dwarf galaxies, faint and small. But there is one other giant, our great companion, the Andromeda Galaxy, sitting about 2.5 million light-years away. When you look at Andromeda through a telescope, You are seeing light that left it 2.5 million years ago, before our own ancestors looked anything like us. And here is something that surprises most people. Andromeda is not drifting away from us. It is falling toward us at about 70 miles every second on a slow collision course. In roughly 4.5 billion years, the two giant galaxies will meet and merge into one. The night sky is not as permanent as it looks. It is a single frame of a film that runs over billions of years. Now, zoom out again, past the local group, and the structure gets larger and stranger. Our local group is part of a much bigger collection called the Virgo supercluster. And then, in 2014, astronomers, led by Brent Tully, redrew the map entirely. They traced the way galaxies flow, the directions they drift under gravity, and discovered that our supercluster is just one lobe of something far bigger, a single connected basin of galaxies they named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is about 520 million light-years across, and it contains the gathered weight of 100,000 galaxies, all of them slowly streaming toward a gravitational low point called the Great Attractor. We did not even know we lived inside this structure until a decade ago. We had to map the motion of 100,000 galaxies just to learn the name of the place we have always called home. And Laniakea, immense as it is just one feature on a map that keeps going. When you pull back far enough to see hundreds of millions of light-years at once, the universe reveals its true body, and it does not look like scattered dust at all. It looks like foam. It looks like a network of threads, what astronomers call the cosmic web. Galaxies are strung along enormous filaments, like droplets of water clinging to a spider's silk. Where filaments cross, galaxies pile up into dense clusters. And between the threads lie the strangest regions of all, the cosmic voids, enormous rounded emptinesses where there is almost nothing for hundreds of millions of light-years in any direction. I want to stop on those voids for a moment, because they are easy to skip past, and they are quietly terrifying. There is a region called the Boötes Void, sometimes nicknamed the Great Nothing, which is about 330 million light-years across and very nearly empty. If our Milky Way happened to sit at the center of a void like that, our astronomers would have looked up through the early 20th century and seen almost no other galaxies at all. They might have concluded that our galaxy was the entire universe, alone in an endless dark, because the nearest neighbors would have been too far away to notice. Where you happen to sit in the cosmic web shapes what you are even able to discover about the universe. Geography becomes destiny, on a scale of hundreds of millions of light-years. And then there are the largest structures of all, the ones that push at the limits of what should even be possible. There is a feature called the Sloan Great Wall, a sheet of galaxies over 1 billion light-years long. And there is a candidate structure called the Hercules Corona Borealis Great Wall, which some measurements suggest may span as much as 10 billion light-years. Let that number sit next to the ones we built earlier. A single galaxy takes light 100,000 years to cross. This wall of galaxies may take light 10 billion years to cross. It is a structure so large that it begins to rival the size of the observable universe itself. That last fact is not just a piece of trivia, and here is where I have to be honest about a real tension in the science, because I promised you honesty. For more than a century, cosmology has rested on a quiet assumption called the cosmological principle, the idea that on the largest scales the universe is smooth and uniform, the same in every direction, with no special places and no enormous lumps. That assumption is what lets us do the math at all. But structures like the Hercules Corona Borealis Great Wall strain that assumption, because they may be too large to fit comfortably inside a universe that is supposed to be smooth. The argument is not settled. Some researchers think these giant walls are real and a genuine puzzle. Others think they are statistical mirages patterns our eyes and our instruments stitch together out of noise. This is one of those places where the science is still arguing with itself, and I would rather show you the argument than pretend it is resolved. I find it worth pausing on how recently we learned any of this, because it tells you something about where we stand. For almost all of human history, the Milky Way was the universe. As late as the 1920s, serious astronomers argued about whether the faint smudges we now call galaxies were other islands of stars far away, or just clouds of gas inside our own. It was Edwin Hubble, the same Hubble we will meet again shortly, who finally measured the distance to Andromeda and proved it lay far outside our galaxy, that the universe was not one island, but countless islands. That was barely a century ago. The picture of the cosmic web, of Laniakea, of the Great Walls, is newer still, much of it assembled in the last few decades, as our telescopes and our maps improved. We are the first humans ever to see the universe at this scale, and we are almost certainly not seeing the final picture. Every generation of better instruments has revealed that the structures are larger and the architecture grander than the one before. There is no reason yet to think that has stopped, but here is what matters for our climb tonight, and this is the thread I want to tie back to before we move on. Every rung we have stepped on, from the galaxy to the local group to Laniakea to these great walls, is another bubble nested inside a larger one. And we have now climbed so high that the largest structures we can find are starting to approach the size of the entire observable universe. The staircase is running out of room, which means the next question is no longer about finding bigger objects inside the bubble. It is about the bubble itself. Because we have been throwing around this phrase, the observable universe, 93 billion light-years across, as if it were obvious. And it is hiding the single most beautiful paradox in all of cosmology, the one I planted at the very beginning. The universe is younger than the distance across it. It is time, finally, to face why. Is less than break time equals 1s is greater than number, part 4. The paradox of 46 billion. Here is the paradox, stated as plainly as I can make it, so we can stare at it together before we solve it. The universe is 13.8 billion years old. Light travels at a fixed speed, the fastest speed anything can travel. So the farthest any light could possibly have traveled to reach us is 13.8 billion light years, because that is how far light gets in 13.8 billion years. That seems airtight. And yet, when astronomers measure the distance to the edge of what we can see, they do not get 13.8 billion light years. They get about 46 billion. The observable universe stretches roughly 46 billion light years in every direction, which makes it about 93 billion light years across. The light has only been travelling for 13.8 billion years, but the objects that sent it are now sitting 46 billion light years away. How can something be farther away than light could have travelled to reach us? Let me kill the wrong answer first, because it is the one almost everyone reaches for. The wrong answer is that the galaxies must have raced away from us faster than light, moving through space at impossible speeds. That is not what happened. Nothing in this story ever moves through space faster than light. The speed limit you have heard about, the one that says nothing can outrun a beam of light, is real, and it is never broken here. The resolution is far stranger and far more elegant than anything moving fast. The key is to separate two different ideas of distance that we usually let collapse into one. There is the distance the light actually travelled, the length of the road it took, and there is the distance the object sits at right now, today, after all this time has passed. On Earth, these are the same thing. If a friend mails you a letter from a town 100 miles away, the letter travelled 100 miles, and the town is still 100 miles away when the letter arrives. But the universe is not a fixed map with towns sitting still on it. The universe is expanding. The space itself, the distance between things, is stretching, and that changes everything. Picture it this way. Imagine a beam of light leaving a distant galaxy billions of years ago, setting out toward us across the space between. As that light travels, the space it has already crossed is stretching out behind it, and the space still ahead of it is stretching too. The light is swimming through a medium that is constantly growing. So even though the light moves at its fixed speed, the total distance it has to cover keeps increasing while it is in transit. And by the time the light finally arrives at your eye, the galaxy that sent it is no longer where it was. It has been carried much, much farther away by the expansion of space itself, even though the galaxy never moved through space at all. Let me give you the real numbers, because they are almost unbelievable. The oldest light we can see, the light from the very edge of the observable universe, left matter that was, at the time, only about 42 million light-years away from the spot that would become us. 42 million. That is close, in cosmic terms, closer than many of the structures we discussed a moment ago. But that light has been travelling for 13.8 billion years, and while it travelled, space stretched so enormously that the matter which sent it is now about 46 billion light-years away. The same patch of universe was 42 million light-years away when the light left, and is 46 billion light-years away now. The light recorded a journey across a road that grew by a factor of more than 1,000, while the light was still on it. And we can actually see the evidence of that stretching written directly into the light itself. When space expands, it stretches the light travelling through it, pulling its waves longer. Short waves become long waves. Blue light reddens, red light slides into the infrared, and infrared slides into microwaves. We call this redshift, and it is the fingerprint of expansion. The oldest light we can see has been stretched by a factor of about 1,100. It left as a fierce glow and arrives as faint microwaves, its waves pulled out more than 1,000-fold by the growth of space. When we measure that stretch, we are literally measuring how much the universe has expanded since the light began its journey. The redshift is not a guess. It is a ruler, and it reads more than 1,000. Now here is the consequence that genuinely bends the mind, the one I want you to carry forward. Because space is expanding, and because the expansion adds up over enormous distances, there are galaxies whose distance from us is growing faster than the speed of light. Right now, as you lie there are galaxies receding from us faster than light itself. And I just told you, nothing can move faster than light. So let me be careful, because both things are true at once. Nothing moves through space faster than light, but space itself can stretch as fast as it likes. The galaxies are not racing through space. They are sitting more or less still in their own neighborhoods. It is the space between us and them that is being created, faster and faster the farther out you look, until at some distance, the sheer accumulation of stretching space carries them away faster than any light could ever close the gap. This leads to something almost paradoxical inside the paradox. There are galaxies we can see right now whose ancient light is arriving at our telescopes tonight that are at this very moment receding from us faster than light. We see their past, the light they sent long ago when they were closer, and the expansion had not yet carried them beyond that threshold. But their present is already unreachable. The light they are emitting tonight will never, ever reach us. We are looking at ghosts, in a sense, at galaxies whose current selves have already slipped past the point of no contact. Hold on to that, because it is going to come back in a much darker form near the end of our climb. If this still feels like a cheat, like I am sneaking faster than light travel in through a side door, here is the picture that finally made it click for me. Imagine a long rubber band with two ants standing on it, a small distance apart. Now imagine the ant on the left starts walking toward the ant on the right at a fixed, modest pace, the fastest it can go. That is light, moving at its fixed speed. But while the ant walks, you grab both ends of the rubber band and start stretching it. If you stretch it slowly, the walking ant still makes progress and eventually arrives. But if you stretch it fast enough, the band between the two ants grows faster than the walking ant can cover ground, and the ant on the right actually gets farther away over time, even though the walking ant never slows down and never stops trying. The walking ant has not broken any speed limit. It is simply walking on ground that is being manufactured beneath it faster than it can cross. Light in our universe is that walking ant, and space is that endlessly stretching band. Nothing cheats, the road just grows. So the paradox dissolves, but it dissolves into something stranger than the puzzle we started with. The universe is 93 billion light-years across, despite being only 13.8 billion years old. And the entire extra size, that factor of nearly 7, comes from one thing and one thing only. Space has been stretching the whole time. Size and age are not measured in the same currency. They are connected by an exchange rate, and that exchange rate is the expansion of the universe. Which raises the obvious next question, the one that has tormented physicists for the better part of a century. If space is stretching, something has to be doing the stretching. Something has to be paying for all that new distance. And the closer we looked at what that something might be, the more it turned into the single biggest embarrassment in all of modern physics. Is less than break time equals 1s, is greater than. Number. Part 5. The engine that makes the number grow. We have established that space stretches, and that the stretching is the reason the universe is bigger than its age. Now we have to meet the engine that does the stretching, because that engine does not just explain the size we already have. It controls the size the universe will ever reach, and it decides how the whole story ends. To understand the true size of the universe, you have to understand the thing that is busy enlarging it as we speak. The story begins in the 1920s with a quiet Belgian priest and physicist named Georges Lemaitre and an American astronomer named Edwin Hubble. Working separately, they noticed something extraordinary about the light from distant galaxies. The farther away a galaxy was, the more its light was redshifted, the more its waves were stretched. And the stretching followed a clean rule. Twice as far away meant twice as much redshift. The only sensible explanation was that the galaxies were not sitting still in a fixed cosmos. They were all moving apart, and the more distant ones were receding faster, exactly as you would expect if the entire universe were expanding, every point drifting away from every other point. Run that expansion backward in your mind, like rewinding a film, and everything rushes together. The universe had a beginning. It started small and hot and dense, and it has been growing ever since. This was the birth of the idea we now call the Big Bang. For most of the 20th century, the open question was not whether the universe was expanding, but how the expansion would end. Everyone assumed gravity would be the deciding factor. Gravity pulls things together, so the expansion, set off by the Big Bang, ought to be slowing down the way a ball thrown upward slows as Earth's gravity tugs at it. The only question was whether there was enough matter in the universe for gravity to eventually halt the expansion and pull everything back together in a great collapse, or whether the universe would coast outward forever, slowing but never quite stopping. Astronomers built careful projects through the 1990s to measure exactly how fast the expansion was slowing down. They were trying to read the universe's breaks, and then, in 1998, came one of the most genuinely shocking discoveries in the history of science. Two competing teams of astronomers, measuring the light of distant, exploding stars to gauge the expansion across billions of years, found that the expansion was not slowing down at all. It was speeding up. The universe is expanding faster today than it did in the past. Something is not just resisting gravity. Something is actively pushing space apart, harder and harder, accelerating the growth of the cosmos. The discovery was so unexpected and so well measured that it earned the Nobel Prize in 2011. And it left physics with a problem it has not solved to this day. We gave that something a name. We call it dark energy. But I want to be completely honest with you about what that name means, because the name is dressed up to sound like knowledge, and it is really a confession of ignorance. Dark energy is not a substance anyone has ever detected directly. It is not something we understand. It is simply the placeholder label we attach to whatever is causing the expansion of the universe to accelerate. And here is the part that should astonish you. When physicists add up the energy budget of the entire universe, this mysterious dark energy makes up about 68% of everything. More than 2/3 of the universe is a thing we named but cannot explain. All the ordinary matter, every star and planet and person and grain of dust, every galaxy in those great walls we climbed through, all of it together is less than 5% of the total. We have written a thorough account of the universe's size and history, and the main character is a stranger whose face we have never seen. The simplest guess for what dark energy is comes, oddly enough, from a mistake Einstein made and then regretted. When Einstein first wrote his equations for gravity in the universe, he added a term he called the cosmological constant, a kind of built-in pressure of empty space, because he wanted a universe that stayed still. When Hubble showed the universe was expanding, Einstein threw the term out and reportedly called it his greatest blunder. But the cosmological constant came back, because a constant energy woven into the fabric of empty space is exactly the kind of thing that would push space apart at an accelerating rate. For decades, this has been the standard assumption. Dark energy is constant, the same everywhere and at all times, an unchanging property of space itself. But now, I get to tell you something genuinely fresh, because the universe rarely lets us keep our tidy assumptions for long. In March of 2025, a project called the Dark Energy Spectroscopic Instrument, or DESI, released the results of the largest three-dimensional map of the universe ever made, charting the positions of nearly 15 million galaxies and quasars across about 11 billion years of cosmic history. The point of the map was to watch how the expansion has behaved over time, and to test whether dark energy really is the unchanging constant we assumed. And the data delivered a surprise. When combined with other measurements, the map hinted that dark energy may not be constant after all. It may be weakening, very slightly, over cosmic time. I have to flag this carefully, the way the scientists themselves do. This is a hint, not a confirmed discovery. The signal sits at a level of confidence that demands more data before anyone can claim certainty. But if it holds up, it would overturn the simplest picture of the universe and rewrite the ending of the entire story. Why does it matter so much for our question about size? Because the behavior of dark energy decides how much universe we will ever be able to reach and what the final state of everything will be. If dark energy is a true constant, the expansion accelerates forever, and the reachable universe keeps shrinking until each surviving island of galaxies is utterly alone. If dark energy is weakening, the future could look very different, perhaps even reversing one day into a collapse. We do not know which future is ours. And there is a second crack in our certainty I should mention, called the Hubble tension. When we measure the current expansion rate using the ancient light from the early universe, we get one number, about 67. When we measure it using nearby exploding stars and other local methods, we get a noticeably higher number, to about 73. These two numbers should agree. They stubbornly do not, and the disagreement has only sharpened as the measurements have improved. We cannot perfectly agree on how fast the universe is expanding right now, which means we cannot perfectly agree on its exact size and age either. I want to dwell for a moment on how strange it is that we are this confused about the majority of the universe, because it is a genuinely humbling thing to sit with. We have mapped the positions of millions of galaxies. We have measured the temperature of the universe to 1,000th of a degree. We have weighed atoms and split them and traced the chemistry of stars that died before the sun was born. By almost any measure, our knowledge of the cosmos is one of the great achievements of our species. And yet, when we add it all up, more than 95% of the universe is in forms we cannot explain. 68% is this dark energy pushing space apart. Another 27% or so is dark matter, a separate mystery, some unseen substance whose gravity holds galaxies together, but which we have never directly caught. The ordinary stuff, the atoms, the light, everything we have ever touched or seen, is a thin froth on top of an ocean of the unknown. When we ask how big the universe is, we are asking a question whose answer is governed almost entirely by things we have named but do not understand. That is the honest position we argue from. So here is the thread, tied tight before we move on. The expansion engine, this thing we call dark energy, is the single reason the universe is bigger than its age, and it is also the reason the part we can ever touch is quietly shrinking. Everything we are climbing toward tonight, every one of the 4 sizes, runs through this one mysterious force. Dark energy, set the size we have, it is enlarging that size as we speak, and it will decide the size we are left with at the end of time. Which means before we can ask how big the whole universe is, we have to find the wall, the actual outer limit of everything we are able to see. And that wall, it turns out, is not made of matter at all. It is made of something far stranger. Is less than break time equals 1s, is greater than, number, part 6, the wall at the edge of sight. We keep using this phrase, the observable universe, as if its boundary were obvious, a clean circle drawn somewhere out in the dark. So let us go and actually find that boundary and look at what it is made of, because the answer is one of the most beautiful things in all of science, and almost nobody who has not studied it would ever guess it. To find the edge of what we can see, we have to travel back to the universe's infancy, to a time long before the galaxies and the great walls existed. In the beginning, the universe was not just hot. It was so hot and so dense that ordinary matter as we know it could not exist. Atoms could not hold together. Instead, the universe was filled with a glowing plasma, a fog of bare atomic nuclei and free electrons, all of it crammed together and seething. And here is the crucial fact about that fog. Light could not travel through it. A beam of light trying to cross the early universe would scatter off a free electron almost immediately, and then off another, and another, bouncing endlessly, never getting anywhere. The early universe was opaque, glowing from within but blind, like the inside of a thick cloud lit by lightning, where the light cannot escape and you cannot see through it. This fog lasted for about 380,000 years. Then something changed, and it changed the universe forever. As the universe expanded, it cooled, the way any gas cools when it spreads out. And at a certain temperature, the universe became cool enough for the first time for the electrons to settle down and bind to the nuclei, forming the first complete stable atoms. We call this moment recombination. And the instant it happened, the fog cleared. With the free electrons now locked up inside atoms, there was nothing left to scatter the light. Suddenly, for the first time in cosmic history, light could stream freely across the universe. The cosmos went from opaque to transparent in a geological blink, and the light that was set free in that moment has been travelling ever since. That light is still arriving today. It comes at us from every direction in the sky, the oldest light there is, released the moment the universe became clear. We call it the cosmic microwave background. It is the single most important thing in this entire video, so let me tell you exactly what it is in terms of our climb. The cosmic microwave background is the wall of the observable universe. It is the literal edge of what we can see. When you look out into space in any direction, you are looking back in time, and if you look far enough, you eventually reach the moment the fog cleared, 380,000 years after the beginning. You cannot see past it, because before that moment the universe was opaque. There was no free light to see. The wall is not a wall of brick or matter or even a place. It is a surface of time, the boundary of the era when light was first able to travel. Astronomers call it the surface of last scattering, the spot where that ancient light bounced off matter for the final time before sailing free toward us. Now sit with the geometry of this, because it is genuinely dizzying. The wall is not off in one direction. It surrounds you completely, in every direction at once, like the inside of an immense sphere with you at the center. And it is the same wall everyone sees, no matter where they are. Every observer, anywhere in the universe, sits at the center of their own sphere of ancient light. The wall is about 46 billion light-years away from us today, carried out to that distance by the same expansion of space we discussed, even though the light that makes it left from much closer. And, because it marks the youngest moment we can see, looking at the wall in any direction means looking at the universe when it was only 380,000 years old, a newborn compared to its present age of nearly 14 billion years. The farthest thing we can see is also the youngest thing we can see. The edge of space and the edge of time are the same surface. This light was discovered almost by accident, which I always find a lovely detail. In 1965, two researchers named Arno Penzias and Robert Wilson were working with a sensitive radio antenna and kept picking up a faint hiss they could not get rid of, a signal coming from every direction in the sky. They checked their equipment. They cleared out the pigeons that had nested in the antenna. The hiss remained. What they had stumbled onto was the cosmic microwave background, the cooled and stretched remnant of that first free light, redshifted by the expansion of the universe across nearly 14 billion years until its fierce original glow had been pulled all the way down into faint microwaves, a whisper at about 2.7 degrees above absolute zero. They won the Nobel Prize for noticing a hiss they could not silence. And in the decades since, satellites named COBE, WMAP, and Planck have mapped that ancient light in exquisite detail, charting tiny ripples in its temperature, differences of 100,000th of a degree from place to place. Those ripples are the seeds. The slightly denser spots in that infant light are the places where gravity later gathered matter into the filaments and clusters and great walls we climbed through earlier. The largest structures in the universe were written, faintly, into the very first light. There is something almost tender about how uniform that ancient light is, and it is worth understanding why it matters. When we map the cosmic microwave background across the entire sky, the temperature is astonishingly even, the same to about 1 part in 100,000 in every direction. The whole sky, all of it, glows at the same gentle 2.7 degrees above absolute zero, with only the faintest freckles of warmer and cooler. Think about what that uniformity is telling us. Regions on opposite sides of the sky, regions that are now separated by more than 90 billion light-years and have never been in contact in the entire history of the universe, somehow have almost exactly the same temperature. It is as if you walked into a building you had never visited and found every room, in every wing, set to precisely the same warmth, with no shared thermostat and no way for the rooms to have ever communicated. That puzzle, the strange sameness of the early universe, is one of the main reasons physicists came to believe in inflation, that burst of impossibly fast expansion in the first instant, which would have stretched a single, tiny, uniform patch out to become everything we see. The wall does not just mark the edge of sight. It carries, written in its faint freckles, the fingerprints of the universe's first moments. But the wall raises a question that should make the back of your neck prickle. We cannot see past the cosmic microwave background in light, because before that moment there was no free light to carry an image. So is the wall the true edge of everything? Is that the size of the universe, full stop? And the answer is no, and this is where most people's intuition quietly breaks. The wall is only the edge of what we can see. It is a limit on our sight, set by the speed of light, and the age of the universe and the era when the fog cleared. It is not the edge of what exists. There is almost certainly universe beyond the wall, more space, more galaxies, more great walls, stretching on past the boundary of our vision. We just cannot see it, because the light from out there has not had time to reach us, and the oldest light we can ever catch is the light from the fog clearing, not from anything farther out. There are, in principle, two ways we might one day peek behind the wall. The Big Bang should have released not only light, but also a flood of ghostly particles called neutrinos, which barely interact with anything and could, in theory, carry information from before the fog cleared. And the violent first instance should have sent out ripples in the fabric of space itself, primordial gravitational waves, which would also predate the wall of light. We are only beginning to learn how to chase these things. They are among the great frontiers of the next century of physics. But even they would only push the wall back a little toward the very first instant. They would not show us the universe beyond our horizon, the universe whose light will never arrive. So here is the open door we walk through next. We have found the wall, the edge of the seeable, made not of matter but of the moment light was born. We have admitted that there is more universe on the other side of it. But what does it even mean for there to be an other side, for something that may have no edge at all? Before we can ask how big the whole universe is, we have to dismantle the most stubborn picture in your mind, the one where the universe is a box with a wall you could fly to and peer over. Because that picture is not just wrong, it turns out to be impossible. Is less than break time equals 1s, is greater than number. Part 7. The Galaxies That Shouldn't Exist Yet. Before we dismantle that picture, I want to take you on a short stop right up against the wall, to the very frontier of what our best telescope can see, because something is happening out there that nobody fully expected, and it speaks directly to the strange unity of distance and time we just discovered. The James Webb Space Telescope was built, in part, to look as close to the wall as possible, to catch the faint, stretched light of the first galaxies forming in the early universe, just after the cosmic dark ages ended and the first stars switched on. In 2025, it found a record breaker, a galaxy given the name MOM-Z14. Its light has been stretched by an enormous redshift of about 14.4, which means we are seeing this galaxy as it was when the universe was only about 280 million years old, a tiny fraction of its current age. The light from MOM-Z14 has been travelling toward us for something like 13.5 billion years. When that light set out, there was no Earth, no Sun, no Milky Way as we know it. The galaxy is so far away that it sits near the very limit of what is visible in front of the wall, almost as far back as we can look before light itself runs out. And here is what makes it more than a record. MOM-Z14 should not look the way it does. By the rules astronomers had written for how galaxies grow, a galaxy this early should be small, faint, and chemically simple, made of little more than the hydrogen and helium left over from the Big Bang. Instead, this galaxy is surprisingly bright, surprisingly dense, and already enriched with heavier elements, the kind of chemistry that normally takes many generations of stars to build. It is tiny, only about 240 light-years across, hundreds of times smaller than our own galaxy, and yet it is far more developed than its age should allow. It is not alone in this. The Webb telescope keeps finding galaxies in the early universe that look too grown up, too quickly, as if the cosmos assembled its structures faster than our models said it could. I want to be careful here, because this is exactly the kind of fact that gets twisted into claims that scientists have been proven wrong about everything. They have not. The models are being revised, not thrown away. This is how science is supposed to work. The universe handed us a surprise, and now theorists are busy figuring out how the first galaxies could have grown up so fast. It is a genuine open puzzle, and it is being worked on, not buried. But there is a poetry to it that ties straight back to our climb. To look at the most distant galaxies is, unavoidably, to look at the youngest universe. Distance and time are not two separate things out here. They are the same axis, the same direction. The farther out you point the telescope, the further back into the past you see. Mumsy 14 is both the most distant confirmed galaxy and one of the youngest objects we have ever witnessed. And those two facts are not a coincidence. They are the same fact. And here is the thread I want you to hold as we step off this frontier and into the strangest part of the whole climb. Even Mumsy 14, the most distant thing humanity has ever confirmed, the galaxy seen almost at the dawn of light, still sits inside our bubble. It is still in front of the wall, still within the observable universe, still part of the small sphere we can see. The most distant object we have ever found is, in the scale of what is coming next, practically a neighbour. Because in the next part, we are going to stop looking for distant objects inside the bubble and start asking about the bubble itself and whether the thing we have been calling an edge is an edge at all. Is less than break time equals 1s? Is greater than number, part 8. There is no edge in space. I want to take aim at the most stubborn picture you are probably carrying because almost everyone carries it, and it is wrong in a way that matters. The picture goes like this. The observable universe has an edge, that wall we found, about 46 billion light-years out. And on the far side of the edge, there must be either more universe, with a true outer boundary somewhere, a final wall, or there must be nothing, an empty void into which the universe is expanding. You imagine that if you flew far enough, fast enough, you would eventually arrive at the edge of everything and be able to peer over it. I am here to tell you that this picture is not just unproven. It is impossible. There is no edge in space to fly to, and there is nothing the universe is expanding into. Let me start with the hardest part, the thing about the Big Bang that almost every popular account gets subtly wrong. The Big Bang was not an explosion that happened at a particular point in space, throwing matter outward into a surrounding emptiness. That is the image the name conjures, a bomb going off in the middle of a dark room, but it is misleading. The Big Bang happened everywhere, all at once. There was no center to it, no single spot where it occurred, because space itself was part of what was expanding. Every point in the universe was once crammed together with every other point, and then space everywhere began to stretch. The expansion is not matter flying apart inside space. It is space itself growing, at every location simultaneously. There is no point you could travel to and say, here, this is where it all began, because it began at every here there is, including the one where you are lying right now. This is why the universe has no center. We tend to assume that if everything is expanding away from us, then we must be at the center of the expansion. But every observer, everywhere, sees exactly the same thing. From any galaxy in the universe, all the other galaxies appear to be receding, and the more distant ones recede faster, and the observer naturally feels themselves to be at the center. There is a classic way to picture this. Imagine a loaf of raisin bread rising in the oven. As the dough expands, every raisin moves away from every other raisin. Pick any raisin and look around, and you will see all the others retreating from you, with the farthest ones retreating fastest. But no raisin is the center of the loaf's expansion. They are all simply being carried apart by the growing dough between them. The universe is like that, except there is no crust, no outer edge of the loaf at all. The dough goes on as far as there is dough. So what, then, is the observable universe's wall, if it is not a true edge? The answer is that it is a horizon. And a horizon is a very particular kind of boundary. Think about standing on a ship in the middle of the ocean and looking out at the horizon. You can only see so far, maybe a dozen miles, before the curve of the earth hides the rest. That horizon looks like an edge, a circle of boundary around you, but it is not the edge of the ocean. It is just the limit of your sight line. The ocean continues far beyond it, and if you sail toward the horizon, it retreats. You never reach it, because it is not a place. It moves with you. The edge of the observable universe is exactly this kind of thing. It is the limit of how far light has had time to travel to us in the age of the universe. It is a horizon of information, personal to each observer, not a wall standing in space. And this leads to the idea that, for me, is the strangest of the entire climb, so I am going to say it slowly. Your observable universe and mine are slightly different. We are close together, you and I, so our bubbles overlap almost perfectly. But imagine a being living in a galaxy near the edge of our observable universe, 40 billion light-years away. That being has its own observable bubble, its own horizon of 46 billion light-years in every direction, centered on itself. Half of its bubble overlaps with ours. The other half reaches into regions we will never see, regions beyond our horizon entirely. And now imagine a being twice as far away, 100 billion light-years from us, out past the limit of anything we can ever detect. Its observable universe and ours share nothing at all. Not one galaxy, not one star. It has a complete, full universe to look at, billions of galaxies, its own ancient wall of light, and none of it is anything we could ever see, and none of what we see is anything it could ever see. There is no contradiction in this. There are simply countless overlapping bubbles, each one centered on its own observer, tiling a universe that may have no edge anywhere. There is one more subtlety I have to add, because it sets up something important and a little cruel that is coming. You might think the observable universe simply grows over time, that as the universe ages, more and more distant light has time to reach us, so our bubble steadily widens and we get to see more. And in one sense that is true. The horizon of what we can see does creep outward as the universe ages. But remember the expansion engine, the dark energy from a few rungs ago. The accelerating expansion is working against us. It is carrying distant regions away faster than their light can cross to us. So while the seeable universe creeps slowly outward, the reachable universe, the part we could ever travel to or send a signal to, is actually shrinking. We can see more, in a sense, but we can touch less. Hold that contradiction. It is going to define the future of everything. I know the raisin bread and the ocean horizon are only analogies, and analogies always break somewhere. So let me be honest about where these ones strain, because the place they break is itself instructive. When I describe the raisin loaf, you naturally imagine looking at it from outside, seeing the whole loaf sitting in an oven, in a kitchen, in a house. But there is no outside to the universe, no kitchen it sits in, no vantage point from which you could see the whole thing at once. The expansion is not something happening to the universe as seen from somewhere else. It is something happening within it, the only thing there is, with no exterior at all. That is the part our minds simply refuse to hold, because every object we have ever encountered has had an outside, a surrounding, a place it sits within. The universe is the one thing that does not. It is not a big object in a bigger space. It is the space, and the space goes as far as it goes, and there is no balcony anywhere from which a viewer could look back and say, "Ah, so that is its shape." Even the cleverest analogy smuggles in an outside, and the strangest fact about the universe is that there isn't one, so we have demolished the picture of the box with a wall. There is no edge in space, no center, nothing the universe is expanding into. What we have is a horizon, a limit on information, beyond which there is almost certainly more universe, possibly an unimaginable amount more, which forces the single biggest question in all of cosmology, the question this whole video has been climbing toward. It is not how far we can see. We have answered that. It is whether the thing we are inside of has any size at all, whether it is finite or infinite. And that question turns out to depend on something you would never expect, the shape of space itself. Is less than break time equals 1s, is greater than. Number, part 9. Flat, curved, finite, infinite. Here we are, at the lowest rung of the climb, the bedrock question the whole title has been pointing at. Is the universe finite, with some enormous but countable size, or is it infinite, going on without end in every direction forever? And the astonishing thing is that this question, which sounds like pure philosophy, is actually a question about geometry. It comes down to the shape of space on the largest scales. Get the shape, and you get the answer. There are three basic shapes space can have, and I want to give you a way to feel each one. The first is positively curved space, which is like the surface of a ball. On the surface of a sphere, if you set off in a straight line and keep going, you eventually come back to where you started, and the surface has a finite area even though it has no edge. A positively curved universe would be finite, closed, wrapping back on itself. The second shape is negatively curved space, like the surface of a saddle or a Pringle, curving away from itself in every direction. A negatively curved universe would go on forever, infinite and open. And the third shape is flat space, the ordinary geometry you learned in school, where parallel lines stay parallel forever and the angles of a triangle add up to exactly 180 degrees. A flat universe, if it does not wrap around on itself, is also infinite, endless in every direction. So, which one do we live in? Remarkably, we can measure this. The trick is to find a triangle so enormous that the curvature of space, if there is any, would show up in its angles. And the universe handed us the perfect tool, that wall of ancient light we found earlier, the cosmic microwave background. The ripples in that ancient light have a known physical size, set by the physics of the early universe. We know how big those hot and cold spots really were when the light was released, and we can measure how big they appear in our sky. By comparing the true size to the apparent size, we are effectively measuring the angles of a triangle that spans nearly the whole observable universe. If space were positively curved, the spots would look slightly larger than they should. If negatively curved, slightly smaller. If flat, they would look exactly their true size. The measurements, refined by the Planck satellite and others, give a clear answer, at least for our local patch. Space is flat, not approximately flat. Flat to within a margin of about 0.25%. As far as we can measure, parallel lines in our universe stay parallel, and the great cosmic triangle has angles that add up to a straight 180 degrees. And here is what that flatness implies, the conclusion that should make you sit up. If the universe is truly flat, and if it does not secretly wrap around on itself, then it is infinite, endless. It contains an infinite number of galaxies, an infinite number of stars, going on forever in every direction with no boundary anywhere. The best measurement we have of the shape of space is consistent with a universe that has no size at all because it never ends. But I promised you honesty, and honesty requires several large warnings here, because this is exactly the kind of conclusion that is easy to overstate. The first warning is that a measurement of flatness always comes with a margin of error, and within that margin, a very slight positive curvature is still allowed. If space is just barely positively curved, too gently for us to detect, then the universe is finite after all, but it would have to be enormous, far larger than the part we can see. The mathematics of those gentle curvatures suggests that, if the universe is closed, it must be at least a few 100 billion light-years across, and quite possibly very much larger than that. So even the finite option is not small. The finite option is a universe so large that the entire 93 billion light-years we can see is a minor province within it. The second warning is more subtle and more interesting. Space could be flat and still be finite if it has an unusual shape, what mathematicians call its topology. Imagine an old video game where, when your spaceship flies off the right edge of the screen, it reappears on the left, and when it flies off the top, it reappears at the bottom. The screen is flat. The geometry on it is perfectly ordinary. And yet the space is finite, and it wraps around on itself with no edge anywhere. The three-dimensional version of this is called a three-torus, and a universe shaped like that would be flat, finite, and edgeless all at once. If we lived in such a universe, and if it was small enough, we might be able to see the same galaxy in more than one direction, its light having wrapped all the way around the cosmos. We might even see the same patterns repeating in different parts of the wall of ancient light, what astronomers call circles in the sky. People have searched for exactly that. They have combed the cosmic microwave background, looking for repeating patterns, matched circles, any sign that the universe wraps around and we are seeing the same regions twice. And so far, they have found nothing. No repeats, no matched circles, no evidence that space closes back on itself within the range we can check. Now, finding nothing does not prove the universe is infinite. It only proves that if the universe wraps around, it does so on a scale larger than the part we can observe. It sets a floor under the size, a lower bound, but it can never set a ceiling. You can prove a universe is at least a certain size. You can never prove it is infinite, because no matter how far you see, infinity always lies beyond. And that points to the most fundamental limitation of all, the one I find the most humbling. We can only measure the shape of space inside our own bubble, inside the observable universe. But a universe vastly larger than what we can see would look flat to us no matter what its true global shape was. For the same reason the Earth looks flat to an ant standing in a field. The ant cannot see the curve because the curve is too gentle across the tiny patch it can survey. If the whole universe is far larger than our horizon, and it almost certainly is, then its true overall shape may be permanently beyond our reach, hidden behind the wall of light we can never see past. We could be living on a gently curved cosmos and have no way, ever, to tell it apart from an infinite flat one. Why do so many cosmologists, when pressed in a quiet moment, lean toward infinite rather than finite? It comes back to inflation, that theory of the universe's first instant. If inflation really happened, and the evidence in the cosmic microwave background suggests something like it did, then it stretched space by an almost incomprehensible factor, in a sliver of a second, far more than enough to flatten any curvature the universe might once have had, and to push its true size enormously beyond our horizon. A balloon inflated to the size of the Earth would look flat to anyone standing on it, not because it has no curve, but because the curve has been stretched out beyond detection. Most versions of inflation naturally produce a universe vastly larger than the observable part, and many of them produce one that is, for all practical purposes, infinite. So the lean toward infinity is not wishful thinking or poetry. It is what the leading theory of cosmic origins tends to predict. But I have to stress, again, that this is a theoretical inclination resting on a theory we cannot fully confirm, not a thing anyone has measured. We are reasoning about the shape of the whole from the tiniest sample of it, and reasoning honestly means admitting how thin that sample is. So let me give you the honest answer to the title's question, the real one, the one I have been climbing toward all night. The true size of the universe is one of two things, and we do not know which. Either it is finite, but so enormous that the part we can see, that 93 billion light-years, is a single grain in a structure hundreds of billions of light-years across or more. Or it is infinite, without any size at all, endless in every direction, holding an unlimited number of galaxies and stars and worlds. The measurements lean toward flat, and many cosmologists, partly because the leading theory of the universe's first instant, called inflation, tends to produce a cosmos enormously larger than what we see and very nearly flat, quietly suspect the answer is infinite. But that is a lean, an inclination, not a proof. We are standing at the edge of what can be known, looking out at a question that may never have a final answer. And if the universe really is infinite, then something follows that is almost too strange to say out loud, a consequence that turns the question of size into a question about you. Because in an infinite universe, the mathematics forces a conclusion that sounds like science fiction, but falls straight out of taking infinity seriously. That is where we are going next. But first, I have to tell you about the cruelest twist in the whole story, the one that proves the universe is not getting larger for us at all. It is getting lonelier. Is less than break time equals 1s, is greater than number, part 10. The universe is getting lonelier. We have spent this whole climb watching the universe get bigger, rung by rung, until we reached a size that may have no end. So it would be natural to assume that the future holds even more, that as time goes on, we will see farther and reach more, that the cosmos is opening up before us. The truth is the exact opposite, and it is one of the lonelier facts in all of science. The part of the universe we can ever reach is not growing, it is shrinking. And one day, almost everything will be gone from view. Remember the expansion engine, the dark energy accelerating the growth of space. Because that expansion is speeding up, there is a distance beyond which galaxies are being carried away from us faster than their light can ever cross back to us. That distance is called the cosmic event horizon, and it sits a good deal closer than the edge of what we can see, somewhere around 16 billion light-years. Any galaxy beyond it is lost to us forever. Not just hard to reach, impossible to reach, in principle, even with infinite time and a ship that could travel at the speed of light, we could never get there, and we could never send so much as a single message that would arrive. The accelerating expansion has already sealed those galaxies off from us, permanently. And here is the part that genuinely aches. Of the roughly 2 trillion galaxies in the observable universe, the overwhelming majority have already crossed beyond that horizon of reachability. We can still see them, because their old light, sent long ago when they were closer, is still arriving. But they are already gone to us in every way that counts. We are looking at portraits of galaxies we could never visit, could never contact, could never affect, or be affected by, ever again. The light is a memory. The galaxies themselves have slipped away. Now run the clock forward, far forward, tens and hundreds of billions of years. As the expansion continues to accelerate, more and more galaxies cross the horizon and vanish from reach. The Milky Way and Andromeda and the rest of our local group will merge into a single, enormous island of stars, bound together tightly enough by gravity to resist the expansion. But everything outside that island will recede, redshift, dim, and finally wink out, carried beyond the horizon one by one. There will come an era when an astronomer standing on a planet in that future island galaxy looks out at the night sky and sees only their own stars, no other galaxies, nothing beyond. The rest of the universe will have receded so far and so fast that its light no longer arrives at all. Think about what that means for knowledge. Those future astronomers, however brilliant, would have no way of knowing that the rest of the universe ever existed. They would see a single island of stars surrounded by perfect darkness, and the most reasonable conclusion available to them would be that their galaxy is the whole of creation, eternal and alone. The cosmic microwave background, that ancient wall of light that taught us the universe began in a hot, dense state, will itself have stretched and faded beyond the point of usefulness. The single most important clue to the universe's origin and size will have been erased by the very expansion it helped us discover. They would be living in a universe that lies to them about its own history, and they would have no way to catch the lie. Which leads to a thought I find oddly comforting, and I want to leave it with you before we take the last speculative step. We live early. We live at a time when the evidence is still in the sky. We can still see the other galaxies, still read the ancient light, still measure the expansion, and infer the enormous, possibly infinite cosmos around us. A creature born 100 billion years too late would be locked out of all of it. So the strange privilege of being alive now, on this small planet, is that the universe is still showing us its true size, while it still can. And here is the thread tied tight. This is the cruelest of the 4 sizes we set out to measure. The whole universe may be infinite, endless, beyond all counting, and yet the part any of us could ever touch is small, and getting smaller every second. That gap between the boundless size of everything and the shrinking scrap we can reach is exactly the vertigo the title promised you. And it gets stranger still, because if that boundless everything really is infinite, then it contains something out there that should not be possible. It contains you, again. Is less than break time equals 1s is greater than number. Part 11. Beyond the Beyond. I want to be completely upfront before this rung, because we are about to step off the solid ground of measurement and onto the high wire of speculation. Everything I am about to tell you is where the mathematics points if you take certain ideas seriously, but none of it is established fact, and thoughtful physicists disagree about whether some of it is even science. I am telling you this not to convince you of it, but because no honest tour of the size of the universe is complete without it. So hold all of this lightly, the way you would hold a strange and lovely idea late at night, without needing to decide whether it is true. Start with the simplest version, the one that follows most directly from what we already discussed. Suppose the universe really is infinite and flat, as the measurements gently suggest. In an infinite universe, there are infinitely many regions, like our own observable bubble, each one 93 billion light-years across, tiled out across endless space. Now, within any one bubble, matter can only be arranged in a finite number of ways. The number is unimaginably large, but it is finite because there are only so many particles and only so many positions they can occupy. And here is the logic that follows, cold and inescapable. If there are infinitely many bubbles, and only a finite number of ways to arrange the matter inside a bubble, then arrangements must repeat. Somewhere out there, far beyond our horizon, there must be a bubble identical to ours, down to the last atom, a copy of this galaxy, a copy of this planet, a copy of you, lying exactly where you are, hearing exactly these words, not a metaphor, a direct consequence of infinity plus finite arrangements. The physicist Max Tegmark even estimated how far away your nearest identical copy would be, and the distance is so enormous it has to be written as a tower of exponents. But in an infinite universe, the distance does not matter. The copy is out there. Infinitely many copies are out there. Then there is the next rung up, which comes from the theory of how our universe began. That theory, called inflation, says the early universe underwent a burst of staggeringly fast expansion in its first instant. And many versions of inflation suggest the process never fully stops everywhere at once. In most of the inflating space, the expansion keeps going, and only here and there does it slow down enough to form a pocket, a bubble universe like ours. If that is right, our entire universe, everything we have climbed through tonight, the great walls, the cosmic web, the wall of ancient light, all of it is a single bubble in an endlessly inflating ocean, and there are other bubbles, other universes, possibly with different physical laws, different strengths of gravity, different particles, perhaps even different numbers of dimensions. We would have no way to reach them or see them. They would be universes in the fullest sense, parallel to our own. And there are rungs beyond even that, at the far edge of respectable speculation. There is the version that comes from quantum mechanics, where every quantum possibility plays out in its own branch of reality. There is the most abstract version of all, the idea that every mathematical structure that could describe a universe is, in some sense, as real as ours. I am not going to dwell on these, because the further up this ladder we climb, the more we leave physics behind and enter philosophy. The point is not to settle which of these is true. The point is, what happens to our original question when the universe turns out to be infinite? Because here is the thread, and it is the strangest turn the title can take. We started by asking how big the universe is, expecting a number, and we have climbed so high that the question has transformed under our feet. Once the universe becomes infinite, size stops being a number at all. The question is no longer how big, because there is no biggest. The question becomes how many? How many galaxies? And the answer is infinite. How many worlds? And the answer is infinite. How many versions of this exact moment, of this exact you? And the answer, if any of this is right, is also infinite. The true size of the universe may not be a measurement waiting to be taken. It may be a door that opens onto a question about how many times everything, including the person watching this, is repeated across an endlessness we will never see. And that is about as far up the ladder as anyone can climb. So let us climb back down, all the way down, to the only rung that you can actually touch. Is less than break time, equals 1s, is greater than number, part 12. Your place in the true size. Let us come back down the ladder now, slowly, one rung at a time, the way we came up. Step down from the multiverse, from the infinite tiling of bubbles and the copies of you scattered across endlessness, back to a single universe. Step down from the question of finite or infinite, past the gentle flatness of space, to the wall of ancient light that surrounds us. Step down from the wall, inward past the most distant galaxies seen at the dawn of time, through the great walls and the cosmic web, through Laniakea and the local group, down to a single ordinary galaxy. Step down through the 100,000-year crossing of the Milky Way, past the empty light years, past the nearest star, in through the Oort cloud and the planets, past the sun 8 minutes away, past the moon a second and a quarter away, down through the sky above your room, to a single person, lying still, listening to you. Now that we have earned them, let me lay the 4 sizes side by side, plainly, the way I could not at the beginning. There is the seeable universe, about 93 billion light-years across, the bubble of everything whose light has had time to reach us. There is the reachable universe, smaller than the seeable and shrinking every moment, the part we could ever touch or signal before the expansion carries it away. There is the total universe, the seen and the unseen together, which is at minimum hundreds of billions of light-years across and may well be infinite. And there is the speculative beyond, the bubbles and branches that may lie outside our universe entirely, where size stops being a number and becomes a question of how many. 4 answers to one simple question. None of them the tidy figure you might have wanted at the start. All of them true at once. It would be easy to end here by telling you how small you are, and it would not be wrong. You are unimaginably small against this. If the entire history of the universe were compressed into a single year, all of recorded human history, every empire and every invention and every life ever written down, would fit into the last 2 seconds before midnight on the final day. Your whole life is a flicker too brief to measure on that calendar. And in space, you are smaller still, a speck on a speck on a speck, in a galaxy that is 1 dot among trillions, inside a bubble that may be a grain of sand on a beach with no end. That is all true, and there is a kind of peace in it, the peace of setting down a burden that was never yours to carry. But smallness is only half of the fact, and I think it is the less interesting half. Here is the other half, the part I want to leave you with as you drift off. In all of that size, in all those light years and all those galaxies and all that possibly infinite space, we have never found anything else that can do what you are doing right now. As far as we know, in the entire observable universe, a human being is the only kind of thing that can hold the size of the universe inside its mind. The cosmos is enormous and ancient and mostly empty and mostly indifferent, and somehow, on one small warm planet, It grew an instrument capable of noticing itself, of measuring its own age, of standing at the edge of what can be known and feeling the vertigo of it. The universe is not just large, it is large, and it produced something small enough to fit in a bed and large enough in mind to wonder how big it all is. Consider what had to happen for this moment to exist at all. The universe had to begin in a hot, dense state and expand for nearly 14 billion years. The first stars had to live and die to forge the carbon and oxygen and iron that you are partly made of, because every atom heavier than the lightest few was cooked inside a star that exploded long before the sun existed. The matter that is now your hands and your eyes, and the part of your brain hearing these words, was scattered across light years, drawn together by gravity, folded into a planet, and arranged, through some process we still do not fully understand, into something that could open its eyes and look back out at the place it came from. You are not separate from the size we have been measuring tonight. You are made of it. You are a small, temporary, self-aware knot in the same cosmic material as the great walls and the ancient light, and for a brief while that knot can think about the whole. The atoms in your body are roughly 14 billion years old. They have been many things. Tonight, improbably, they are a listener. So let me give the title back to you, Gently Turned Around. The true size of the universe does not break your sense of reality by making you nothing. It breaks it by revealing that your sense of reality was always a bubble, a small, cozy bubble built for life on the surface of one planet, useful and warm and far, far too small to hold what is actually out there. And the strange gift of a night like this is that you can, for a little while, stand at the edge of that bubble and look past it. You do not have to hold the whole number. You were never meant to. You only have to have stood at the edge of it for a while. Tonight, before you sleep, the universe may have no measurable end. It may stretch on, flat and endless, holding more galaxies and more worlds and more versions of this very moment than any number could ever count. But of everything in it, across all that size we have climbed tonight, the strangest thing of all might be the one happening right now, wherever you are. Somewhere inside the universe, a small, brief, conscious creature paused in the dark and wondered how big its home really was. And that wondering, that quiet, warm flicker of a mind reaching out towards something it can never fully hold, may be the rarest and most remarkable thing the true size of the universe has ever produced. Rest well. The universe will still be out there in the morning, exactly this large, waiting for you to wonder about it again.